Now we'll continue with section 12.2 on the second page of the notes, and let's look at question 6. We have market research. Researchers wanted to know some information about people and their exercise habits, and they said researchers asked people who exercise regularly whether they jog or walk. 58% of the respondents were male, so we know that the probability of selecting a male is 0.58. I like to write that information down kind of as I get it. We know that 20% of all respondents were male who said they jog. So that tells us that that's the probability if you looked at all the people, say there were 100 people. We don't know how many, but let's say there were 100. If you just randomly picked a person, or we randomly pick 100 people and look at those, 20% of the respondents were male who said they jog. Of those 100 people, 20 of them would have had both the characteristic of being male and jogging. So male and jogging is 0.2. So kind of think of it as having a whole bunch of tags of paper, and if you pull out the tags, 58% of the tags would have male. Throw all those tags back in there, and then if you drew out tags and looked at the condition of whether they're male or female and whether they jog or not, 20% of them would have both conditions on the tags. Now, what do we want to find? Find the probability that a male, so we know that it's going to be a male, respondent jogs. Now, that's different from having a person who is male and jogs. So this is the conditional probability. That's the given. We know that the person or the little slip of paper that we pulled out has a male on it. So we want to find the probability that given that someone is a male, what's the likelihood that he jogs or walks? And we know that if we want to find the conditional probability, we find the probability of jog and male divided by the probability of the given condition, which is the probability of male. And we know both of those. So we know the numerator is 0.2. We know the probability of male is 0.58. And so the quotient of those two comes out to be 0.345. So we have to be very careful about reading a question and see if we're finding an intersection between the two of both conditionings happening at the same time, or if we have one of the conditions being given to us and then trying to find the likelihood of the second event given the first one already occurred. Now, let's look at number 7. A very important type of problem is a graphic picture of our data, and that is working with a tree diagram. If we can draw a tree diagram, it's really to our benefit. Just like if we can draw a Venn diagram, it's to our benefit to be able to picture what's happening in our probability situation. So we have the diagram shows the probability that a day will begin clear or cloudy. So in the morning, clear or cloudy, and we can see that 28% of the time we're saying it comes out clear, 72% of the time it comes out cloudy. And then the probability of rain on days that begin clear or cloudy. Because we definitely know that if it starts out clear, it's not necessarily going to mean we're going to have no rain. Now, in this picture, it shows that the likelihood of rain in this location is very small. Now, these are all conditional probabilities after the first branch. So this is really not the probability of rain. It's the probability of rain given that it's clear. This is the probability of no rain given that it's clear. This is the probability of rain given that it's cloudy. This is the probability of no rain given that it's cloudy. And you can see that if I look at this branch, these two branches add up to 1. These two branches after the clear add up to 1. These two branches after cloudy add up to 1. And that will always be the case in our tree diagram. But if we wanted to find the probability of rain, as we're going to be asked to find in number 9, we can't just simply add these two together. So let's look at what we want to find. We want to find the probability that a day will start out clear. So the probability that starts out clear, and that we end up with rain. So we want this condition to happen, and then we want this condition. And so we know that the idea of that is we would find the probability of clear times the probability of rain given that it started out clear. And if we multiply these two branches of our tree together, that will be exactly the answer that we want. So if we take the 0.28 times the 0.04, that will give us the probability of clear times the probability of rain given that it started out clear. And that product comes out to be 0.0112. And again, we could give that as a percent, we could give it as a decimal, could give it as a fraction. Now we want to find the probability of cloudy and no rain. Now, as you might expect, look at this diagram. We want to find cloudy and no rain, which means we need to find the probability of cloudy, which is 0.72. And then we need to find the probability of no rain given that it started out cloudy, and that is our number right here. So multiplying these two branches together will actually give us the intersection of those two characteristics, and that comes out to be almost 0.5. Now, the next one, I think yours has a conditional on here, which we'll add off to the side here. My sheet is just a little bit different. But let's find the probability of rain. Now, if we want to find the probability of rain, we know there are two ways. The day can start out clear, and then it can rain, or it can start out cloudy and then rain. So, if we multiply 0.28 times 0.04, that's one way we can have rain, or add cloudy, 0.72 times 0.31. And that's our second way to have rain. And so when we multiply those together, or add these two products together, we get 0.2344. So about 23% chance of that happening. Now I added one additional question, and we want to find what is the probability of it being clear given that it's a rainy day. So what's the probability that it actually started out as a clear morning given that you have rain later on in the day? Now we're given the conditional the opposite way. We're given rain given clear right here as 0.04. And so if we want to calculate this probability, we can, but we have to think of what our formula tells us to do. We have to find the probability of the intersection, so the probability of clear and rain, which we already found in number 7, and divide that by the probability of rain, which we just found. So given that you know it rained sometime later in the day, we want to find what the likelihood it was clear in the morning. And so we just found the rain probability. That was 0.2344. And the likelihood of clear and rain we found from number 7. That was 0.0112. And then the quotient of those two will end up giving us what our answer is, which I have comes out to be 0.048. So almost a 5% chance of that happening. So if you have rain in the day in this location, in this particular location, the likelihood that it actually had started out clear in the morning was about a 5% chance. Now, last one on the sheet, number 10. We have 80% of airline flights depart on schedule. So we know probability of depart on time is 0.8. 72% of flights depart and arrive on schedule. So they do both. Depart and arrive on time. That's an intersection. And we want to find the probability that a flight that departs on time also arrives on time. So now we have a given condition that the probability that a flight that departs on time, so we know that this happened. The flight departed on time, so that's its given condition. And we want to find, knowing that a flight departs on time, what's the likelihood it will arrive on time? And so We know we need to find the intersection of the two. I'm just going to write it A and B. So we'll say that's A and that's B. So we have to find the probability of both happening, which we already know is 0.72. And we need to divide that by which one? Probability of A or probability of B? You always want the probability of the conditional, the B. So we already know that the intersection is 0.72, and the probability of B is 0.8, and therefore the quotient of that comes out to be 0.9, so 90% of the time that would happen. Now remember, this probability can never be bigger than 1, so if you do some calculation and you get an answer that's bigger than 1, that doesn't mean you found some event that is kind of miraculous. It means you made an error, made some type of a mistake. And so go back and read the question again and see where your error was. All right, now you're ready to practice.